Right now, as you watch this video, time is flowing forward at exactly 1 second per second. Every atom in your body is aging. Every star in the universe is burning fuel it will never get back. The coffee on your desk is cooling down, and it will never spontaneously heat up again. You remember yesterday, but not tomorrow. This seems so obvious, so natural, that you might never question it. But here's what makes this deeply disturbing. Nowhere in the fundamental laws of physics does it say time must flow forward. Newton's equations work perfectly whether time runs forward or backward. Einstein's relativity treats past and future as equally real. Quantum mechanics describes particles that can tunnel backward through time barriers. The mathematics of the universe is completely symmetric. It doesn't care which direction time points. Yet every single process you've ever witnessed obeys time's forward march with absolute precision. Your coffee never spontaneously heats up. You never grow younger. Broken eggs never reassemble themselves. Scientists call this the arrow of time problem, and it's one of the most profound mysteries in physics. Something in the universe is actively choosing which direction time should flow, moment by moment, everywhere, all at once. And tonight, we're going to discover exactly what that something is. The answer involves the death of stars, the birth of black holes, the ultimate fate of consciousness itself, and a mechanism so fundamental that without it, the concept of causality, of cause and effect, would collapse entirely. We're going to uncover why the universe remembers its past, but not its future, and why this arrow of time is both more fragile and more powerful than you could possibly imagine. Leading physicists like Sean Carroll and Carlo Rovelli have spent decades trying to solve this puzzle. What they've discovered challenges everything we think we know about the nature of reality itself. The universe isn't just a stage where time plays out. The universe actively creates time's direction through a process so subtle and so universal that until recently, we couldn't even detect it happening. This isn't just abstract theory. The mechanism that makes time flow forward is the same force that allows your brain to form memories. That makes evolution possible. That gives meaning to the concept of progress itself. Without it, consciousness as we know it simply couldn't exist. Every thought you think, every decision you make, depends on this cosmic process that's been operating since the first moment after the Big Bang. By the end of this journey, you'll understand why the universe knows which direction time should flow, how it enforces this direction, across every scale from subatomic particles to galaxy clusters, and why this seemingly simple fact about reality is actually the most important thing about existence itself. You'll see why some scientists believe that understanding time's arrow is the key to understanding consciousness, free will, and the ultimate meaning of life in a temporary universe. But this story begins in a place that seems to have nothing to do with time at all, in the study of heat, steam engines, and the simple question of why hot coffee gets cold. From this humble beginning emerged one of the most powerful ideas in all of science, and the first real clue about what's actually happening to time. If you're fascinated by the deepest mysteries of existence and want to understand how the universe actually works, subscribe and hit the thumbs up button. And here is a question that will make sense by the end. If the future doesn't exist yet, how does the universe know not to let you access it? Drop your thoughts in the comments. I'll pin the most mind-bending answer. The story of time's direction is really the story of why anything can happen at all. It's the story of how the universe creates novelty, meaning, and purpose from the raw materials of physics. It's about why you exist in this moment and not some other moment, and why this moment can never come again. Now, let's begin our journey into the heart of time itself, starting with a discovery that seemed completely unrelated to time, but ended up revealing its deepest secret. Chapter 1. Cosmic asymmetry. Time feels like the most fundamental aspect of reality, more basic than matter, more essential than energy, more absolute than space itself. We experience it as an unstoppable river carrying us from past to future, never allowing us to swim upstream, never letting us step into the same moment twice. But if you examine the equations that govern our universe, you'll discover something shocking. Time has no preferred direction. Consider Newton's law of gravity. If you film a planet orbiting a star and then play the film backward, the backward motion obeys Newton's laws perfectly. The mathematics doesn't distinguish between clockwise and counterclockwise orbits, between moving toward the star and away from it. Einstein's general relativity is equally symmetric. A black hole forming from collapsing matter follows the same equations as a theoretical white hole that would expel matter. Though we've never seen a white hole, the math treats both scenarios as equally valid. Even quantum mechanics, despite its probabilistic nature, maintains this time symmetry in its fundamental equations. The Schrödinger equation that governs quantum evolution works just as well running backwards through time. A particle tunneling through a barrier could theoretically tunnel backward through time itself without violating quantum mechanics. At the deepest level of physical law, past and future are treated as equivalent directions. This creates what physicists call the arrow of time problem. If the laws of physics are symmetric with respect to time, why does every process in the observable universe show a clear directional preference? Why do we age rather than grow younger? Why do causes precede effects? Why does heat flow from hot objects to cold ones, but never the reverse? The first clue came from studying steam engines in the 1850s. Rudolf Clausius, investigating how to make steam engines more efficient, discovered something profound about the nature of heat. When a hot object touches a cold object, heat always flows from hot to cold, never the reverse. This seemed obvious, but Clausius realized it revealed something fundamental about reality itself. He introduced the concept of entropy, a measure of how spread out or disordered energy becomes in any system. When heat flows from your hot coffee to the cold air around it, the energy doesn't disappear. It simply becomes more evenly distributed, more disordered, harder to capture and use for work. Clausius discovered that in any isolated system, entropy always increases over time. Always. This principle, known as the second law of thermodynamics, was the first physical law that explicitly distinguished between past and future. Unlike Newton's laws or Einstein's equations, the second law is fundamentally asymmetric in time. It says that systems naturally evolve from ordered states to disordered states, from concentrated energy to dispersed energy, from useful configurations to random configurations. But here's where it gets strange. The second law appears to be statistical rather than fundamental. It emerges from the collective behavior of countless particles, each of which individually obeys perfectly time-symmetric laws. When you have trillions of air molecules bouncing around randomly, the probability that they'll spontaneously organize themselves into regions of different temperatures becomes so vanishingly small that it never happens in practice. Think of it this way. Imagine dropping 1,000 coins. You could theoretically get all heads, but the probability is so low that you'd have to drop those coins continuously for longer than the age of the universe to expect it to happen once. Similarly, your coffee could spontaneously heat up by having all its slower molecules randomly speed up while all the surrounding air molecules slow down. The laws of physics permit this, but the statistical probability is so incredibly tiny that it effectively never occurs. This statistical nature of the second law creates a puzzle. If entropy increase is just about probability, then in a truly fundamental sense, time shouldn't have a preferred direction. Over extremely long time scales, random fluctuations should occasionally cause entropy to decrease. Systems should sometimes spontaneously organize themselves. Time's arrow should sometimes reverse. Ludwig Boltzmann, the Austrian physicist who developed the statistical interpretation of entropy, was deeply troubled by this paradox. He realized that if you wait long enough, any system will eventually fluctuate back to a lower entropy state. In an infinite universe with infinite time, every possible configuration should occur infinitely often. This means there should be moments when entropy decreases, when effects precede causes, when time effectively runs backward. Boltzmann's solution was radical. Perhaps we live in one of those rare fluctuations. Maybe the universe we observe, with its clear arrow of time and consistently increasing entropy, is actually an incredibly unlikely statistical fluke. Maybe we exist during one of the universe's rare moments of spontaneous organization, and time's apparent directionality is just a temporary illusion. This idea, known as the Boltzmann brain paradox, leads to disturbing implications. If our organized universe is just a random fluctuation, then it's far more likely that only your brain, with all its memories of an organized past, spontaneously fluctuated into existence just moments ago. All your memories of yesterday, all evidence of history, all the organized structures you see around, you could be part of an incredibly improbable but temporary fluctuation in an otherwise chaotic universe. Modern physics has struggled with this paradox for over a century. The problem is that while the second law explains why entropy increases in isolated systems, our universe isn't obviously isolated, and it's not obvious why it started with such remarkably low entropy in the first place. The Big Bang appears to have begun with matter and energy in an incredibly organized, low-entropy state. But why? Recent discoveries in cosmology have provided tantalizing clues. The cosmic microwave background radiation shows us the universe as it was 380,000 years after the Big Bang, when it first became transparent to light. But here is the key insight that has emerged from decades of research. The universe's low initial entropy wasn't an accident or a lucky coincidence. It was enforced by the fundamental structure of spacetime itself during cosmic inflation. In the first fraction of a second after the Big Bang, space expanded exponentially, stretching quantum fluctuations to cosmic scales while maintaining an overall low-entropy configuration. This means time's arrow doesn't emerge from statistical mechanics alone. It's built into the fabric of the universe from its very beginning. The cosmos started with a specific temporal orientation that continues to propagate through every physical process. The universe doesn't just accidentally prefer one direction of time. It actively maintains temporal asymmetry through mechanisms we're only beginning to understand. This discovery transforms our understanding of time itself. Rather than being a passive dimension through which events unfold, time appears to be an active feature of reality that the universe continuously creates and maintains. The arrow of time isn't just a consequence of increasing entropy. It is the mechanism by which the universe distinguishes between cause and effect, between memory and prediction, between existence and possibility. But this raises an even deeper question. What exactly is the mechanism that enforces this temporal directionality? How does the universe know which direction time should flow? And how does it maintain this orientation across all scales and all processes? The answer lies in understanding what happens when information tries to flow backward through time, and why the universe systematically prevents this from occurring. Chapter 2: Entropy's Secret Deep. Beneath the familiar experience of time as forward march lies a mechanism so subtle that scientists only discovered it by accident while studying something completely different: the relationship between information and energy. What they found reveals that the universe maintains time's direction through a process that operates at every scale, from quantum interactions to cosmic evolution, continuously creating an invisible barrier that prevents information from flowing backward through time. The breakthrough came in 1961 when IBM researcher Rolf Landauer was investigating the fundamental limits of computation. He was trying to understand the minimum amount of energy required to erase a bit of information from a computer's memory. What Landauer discovered shocked the physics community. Erasing information always generates heat. Always. No matter how perfectly designed your computer, no matter how advanced your technology, destroying information inevitably increases entropy. This connection between information and thermodynamics, known as Landauer's principle, seemed like an obscure technical detail at first, but it revealed something profound about the nature of reality itself. Information isn't just an abstract concept that exists in our minds or our computers. It has a physical quantity as real as energy or momentum. And like energy and momentum, information obeys conservation laws that govern how it can move through space and time. Consider what happens when you form a memory. Your brain doesn't just passively record information about the present moment. It creates new physical structures that encode that information in the arrangement of neurons and synapses. This process requires energy and increases the total entropy of the system. But here's the crucial point. Once that memory exists, it creates a permanent record of which direction time was flowing when it formed. Memories always point backward in time. You remember the past, never the future. This isn't just a limitation of consciousness. It is a fundamental constraint imposed by the physics of information itself. To remember the future, you would need to extract information from later moments and encode it in earlier moments. But this would require information to flow backward through time, which would violate the second law of thermodynamics. James Clerk Maxwell, the Scottish physicist who formulated the laws of electromagnetism, was the first to recognize this deep connection between information and time's arrow. In 1867, he proposed a thought experiment involving a hypothetical being, later called Maxwell's demon, that could sort fast and slow molecules in a gas, effectively decreasing entropy by using information about individual particle motions. Maxwell realized that such a demon could potentially reverse the second law of thermodynamics. By observing which molecules were moving fast or slow, and opening or closing a door accordingly, the demon could sort the molecules into hot and cold regions without doing any work. This would decrease the total entropy of the system, effectively making time run backward for the gas. For over a century, physicists struggled to resolve Maxwell's paradox. The solution finally came when scientists realized that the demon itself must be included in the thermodynamic accounting. To operate, the demon needs memory to store information about each molecule's speed. But according to Landauer's principle, erasing this memory to reset for the next cycle always generates exactly enough heat to compensate for the entropy decrease caused by the sorting. This resolution reveals something remarkable about the universe. Information processing always leaves thermodynamic footprints. Every measurement, every computation, every decision creates irreversible changes in the physical world. This irreversibility is what maintains time's forward direction. The universe can't run backward because doing so would require information to flow from future to past, which is thermodynamically forbidden. But the implications go much deeper than just computer science or consciousness. In 2019, researchers at the University of Oxford made a startling discovery while studying quantum entanglement. They found that quantum correlations between particles always form in ways that respect the thermodynamic arrow of time. When two particles become entangled, the correlation emerges in a direction that increases the total entropy of the universe. This finding suggests that quantum mechanics itself is asymmetric in time, despite the time-symmetric appearance of its fundamental equations. The measurement process that causes quantum wave functions to collapse always produces results that point in the same temporal direction as increasing entropy. Quantum mechanics doesn't just happen to align with thermodynamics, it actively participates in maintaining time's forward flow. The mechanism works through what physicists call decoherence, the process by which quantum systems lose their coherent superposition states when they interact with their environment. Every quantum measurement involves decoherence, and decoherence always increases entropy. This means that the act of measurement itself contributes to time zero, creating an irreversible link between quantum mechanics and thermodynamics. Consider what this means for the nature of reality. Every photon that hits your eye and allows you to see every electron that flows through a wire and powers your devices. Every chemical reaction that occurs in your cells. All of these processes involve quantum measurements that increase entropy and thereby reinforce time's as forward direction. The universe maintains temporal asymmetry, not through some mysterious external mechanism, but through the cumulative effect of countless quantum processes all pointing in the same temporal direction. This quantum thermodynamic arrow of time has been experimentally verified through sophisticated laboratory experiments. In 2017, researchers at the University of Vienna created quantum systems that could be precisely controlled and monitored. They found that even when all external influences were eliminated, quantum processes still showed clear temporal asymmetry aligned with entropy increase. The universe's preference for forward time flow is built into quantum mechanics itself. But perhaps the most remarkable discovery about information and time came from studying black holes. In the 1970s, Stephen Hawking calculated that black holes slowly evaporate by emitting radiation. This Hawking radiation carries energy away from the black hole, causing it to shrink and eventually disappear completely. But Hawking's calculation revealed a disturbing paradox. What happens to the information that originally fell into the black hole? If information is truly conserved in quantum mechanics, then the information content of everything that falls into a black hole should somehow be preserved in the Hawking radiation that eventually escapes. But Hawking's original calculation suggested that this radiation was completely random, carrying no information about what had fallen in. This seemed to imply that information could be destroyed, violating one of the most fundamental principles of physics. The resolution of Hawking's information paradox has revealed profound insights about the relationship between information, entropy, and time. Recent theoretical work suggests that information doesn't actually fall into black holes in the way we originally thought. Instead, it remains encoded on the black hole as surface, its event horizon in a form that gets scrambled and redistributed as the black hole evaporates. This process takes an incredibly long time. For a black hole with the mass of our Sun, complete evaporation would take longer than 1,067 years. But throughout this entire process, information about everything that ever fell in remains encoded in the Hawking radiation, just in an extremely scrambled form. The black hole acts like a quantum computer running in reverse, slowly unscrambling the information and releasing it back to the universe. This discovery has revolutionary implications for our understanding of time and information. It suggests that at the deepest level, the universe maintains a perfect record of its entire history. Nothing is ever truly lost or forgotten. Information about every event, every process, every moment of cosmic evolution remains encoded somewhere in the structure of space and time itself. The universe doesn't just know which direction time should flow. It maintains an active memory of everything that has ever happened, encoded in quantum correlations that span cosmic scales. This quantum memory is what gives the universe its sense of temporal direction. Time flows forward because the universe is continuously writing its own history in the form of irreversible quantum information processing. But this raises an even more profound question. If the universe maintains perfect information about its entire past, what does this tell us about the nature of the future? How does the universe's information processing architecture shape not just the flow of time, but the emergence of complexity, consciousness, and meaning itself? Chapter 3: Quantum Memory, Hidden within every quantum interaction lies a memory system so vast and so precise that it makes every human computer look like an abacus in comparison. The universe is constantly writing its own biography at the quantum level, creating an information archive that spans from the smallest subatomic particles to the largest galactic structures. This quantum memory system doesn't just record what has happened, it actively shapes what can happen next, creating the causal structure that we experience as time's unstoppable forward flow. The discovery of this cosmic memory began with a puzzle about quantum entanglement that seemed to have nothing to do with time. When Albert Einstein first learned about quantum entanglement in the 1930s, he famously called it spooky action at a distance and refused to believe it was real. The idea that two particles could become correlated in such a way that measuring one instantly affects the other, regardless of the distance between them, violated Einstein's understanding of locality and causality. But experiments beginning in the 1970s proved that quantum entanglement is not only real, it's fundamental to how the universe operates. When particles interact, they don't just exchange energy or momentum. They exchange quantum information that becomes permanently encoded in their entangled states. This information persists even after the particles separate, creating lasting correlations that span vast distances of space and time. What scientists discovered in studying these correlations was revolutionary. Quantum entanglement has a built-in temporal asymmetry. When two particles become entangled through interaction, the entanglement pattern always encodes information about which particle was the cause and which was the effect. The quantum correlation itself carries a timestamp that indicates the order in which events occurred. Professor Seth Lloyd at MIT demonstrated this temporal structure of entanglement through elegant laboratory experiments. He showed that when quantum systems interact, they create what he calls quantum records, entangled states that preserve information about the causal sequence of their interaction. These quantum records are absolutely irreversible. Once created, they cannot be undone without violating the fundamental principles of quantum mechanics. This means that every quantum interaction in the universe contributes to an ever-growing archive of temporal information. When a photon from the sun hits an electron in your retina, allowing you to see, it creates a quantum record of that interaction. The electron's quantum state becomes entangled with the photon's history, encoding information about when and where the interaction occurred. This quantum record becomes part of the universe's permanent memory of that moment. The implications are staggering. Every chemical reaction in your body, every neural firing in your brain, every photosynthetic process in every plant leaf, all of these processes create quantum records that become part of the universe's growing information archive. The universe isn't just a stage where events play out. It is a vast quantum computer continuously writing its own memory. But the most remarkable aspect of this quantum memory system is how it scales up. Individual quantum records might seem microscopic and insignificant, but they aggregate to create macroscopic structures with clear temporal direction. When trillions of quantum interactions all point in the same temporal direction, they create what physicists call emergent arrows of time, larger-scale phenomena that inherit the temporal asymmetry of their quantum components. This is how the microscopic reversibility of individual particles gives rise to the macroscopic irreversibility of everyday experience. Your coffee cools down because the quantum interactions between coffee molecules and air molecules create a vast number of quantum records, all pointing forward in time. The collective effect of these quantum memories makes it impossible for the coffee to spontaneously heat up again. Theoretical physicist Juan Maldacena at the Institute for Advanced Study has shown that this quantum memory system extends to the largest scales in the universe. Galaxy formation, star evolution, and even the expansion of space itself create quantum records that preserve information about cosmic history. The cosmic microwave background radiation that fills the universe carries quantum information about conditions in the early universe, encoded in its temperature fluctuations and polarization patterns. But perhaps the most profound discovery about quantum memory came from studying black holes and the nature of spacetime itself. In 2016, researchers realized that the event horizon of a black hole acts like a quantum hard drive, storing information about everything that has ever fallen in. The information isn't stored in the black hole's interior. It is encoded on the two-dimensional surface of the event horizon, holographically preserved in quantum correlations. This holographic principle has revolutionary implications for our understanding of space, time, and information. It suggests that all the information contained in any volume of space can be encoded on the boundary of that volume. Your brain, your body, your entire observable universe, all the information about these systems could theoretically be encoded on a two-dimensional surface surrounding them. The holographic principle means that the universe as quantum memory system is far more sophisticated than anyone had imagined. Information isn't just scattered randomly throughout space. It's organized in a hierarchical, holographic structure that allows the universe to efficiently store and access its entire history. Every region of space acts like a quantum library, containing information about all the events that have occurred within it. This quantum information architecture explains why time has such a clear direction. The universe can't run backward, because doing so would require it to erase its quantum memory and reconstruct past states from future information. But quantum mechanics forbids the destruction of information. Once a quantum record exists, it becomes a permanent part of reality that cannot be undone. Consciousness itself appears to be intimately connected to this quantum memory system. Your ability to experience time as flowing forward depends on your brain's capacity to create and access quantum records of past events, while being unable to access records of future events. The asymmetry between memory and prediction isn't just a limitation of biology. It reflects the fundamental structure of quantum information in the universe. Recent experiments in quantum biology have revealed that biological systems exploit quantum information processing in sophisticated ways. Photosynthesis in plants, navigation in migratory birds, and even certain aspects of neural processing in the brain all appear to involve quantum effects. These biological quantum processes create their own quantum records, integrating living systems into the universe's larger information processing architecture. This integration means that life isn't separate from the physical processes that create time, as our life is an extension of those processes. Biological evolution, ecological adaptation, and the development of consciousness all contribute to the universe's growing quantum memory. Living systems don't just experience time. They actively participate in creating it through their information processing activities. The universe's quantum memory system also explains why the past seems fixed while the future appears open. Past events exist as permanent quantum records encoded in entangled states throughout the universe. These records cannot be changed without violating the conservation of quantum information. But future events don't yet exist as quantum records. They remain in superposition states that haven't yet collapsed through measurement and interaction. This suggests that the future is genuinely open in a way that the past is not. While the laws of physics constrain what can happen, they don't completely determine what will happen. The universe as quantum memory creates a foundation of fixed past events that constrain future possibilities, without eliminating genuine novelty and creativity. But this quantum information architecture raises profound questions about the nature of observation and measurement. If every quantum interaction creates permanent records, what happens when conscious observers are included in the system? How does the act of conscious observation relate to the universe's information processing architecture? The answer reveals something remarkable about the relationship between mind and cosmos. between consciousness and the quantum memory that creates time itself. Chapter 4. Information Paradox. At the heart of quantum mechanics lies a paradox so fundamental that it threatens our understanding of reality itself: the measurement problem. When quantum systems exist in superposition, simultaneously existing in multiple states until measured, what exactly happens during the moment of measurement? The answer to this question reveals how consciousness and information processing are woven into the very fabric of time's forward flow, creating a universe where observation itself becomes part of the mechanism that enforces temporal direction. The puzzle begins with the double-slit experiment, the most famous demonstration of quantum weirdness. When individual electrons are fired at a screen with two slits, they create an interference pattern as if each electron somehow passes through both slits simultaneously. But the moment you place a detector to observe which slit each electron passes through, the interference pattern disappears. The electron appears to choose one slit or the other, but only when someone is watching. This transition from superposition to definite measurement outcome is called wave function collapse, and it appears to be fundamentally irreversible. Once a quantum system has been measured and its wave function has collapsed, you cannot recreate the original superposition state. The measurement process destroys information about the unmeasured quantum possibilities and replaces it with classical information about the measurement result. But here's where the paradox becomes acute. If quantum mechanics is fundamentally reversible, as its mathematical formalism suggests, how can measurement be irreversible? The Schrödinger equation that governs quantum evolution works equally well running forward or backward in time. Yet measurement outcomes seem to break this symmetry, always pointing from quantum uncertainty toward classical certainty, never the reverse. Physicist Hugh Everett III proposed a radical solution in 1957. Perhaps measurement doesn't actually collapse the wave function at all. Instead, Everett suggested every possible measurement outcome actually occurs, each in its own parallel universe. When you measure an electron's position, the universe splits into multiple branches, with each branch containing a different measurement result and a different version of you who observed that result. Everett has many worlds. Interpretation elegantly preserves the reversibility of quantum mechanics. The total wave function of the entire multiverse continues to evolve according to the Schrödinger equation without any collapse. But it achieves this preservation at the cost of creating an infinite number of parallel realities, most of which remain forever inaccessible to any single observer. More importantly for our understanding of time's arrow, the many worlds interpretation reveals something profound about the relationship between information and observation. In Everett's formulation, what we call measurement is really the process by which an observer becomes quantum entangled with the system they re-observing. Your brain doesn't just passively record the measurement result. It becomes part of a larger quantum system that includes both observer and observed. This entanglement process has a clear temporal direction. When your brain becomes entangled with a quantum system through observation, information flows from the quantum system to your brain, where it gets encoded in neural structures that constitute memory. But this information transfer is irreversible. Once the entanglement is established, you cannot extract the information from your brain and use it to reconstruct the original quantum superposition. Max Tegmark at MIT has calculated the precise timescales involved in this process. When a quantum system interacts with a macroscopic measuring device like a detector or a brain, decoherence occurs incredibly rapidly, typically within 10 to 23 seconds for systems at room temperature. This decoherence time is so fast that it effectively makes the transition from quantum to classical behavior instantaneous from any practical perspective. The speed of decoherence explains why we never observe quantum superpositions in everyday life. By the time a quantum system becomes large enough to be directly observable, it has already become entangled with countless environmental particles, causing its wave function to collapse into classical behavior. The boundary between quantum and classical worlds is unsharp. It is a gradual transition zone where information flows from quantum uncertainty to classical certainty. But the most remarkable aspect of this transition is that it contributes directly to the universe's arrow of time. Every measurement, every observation, every instance of decoherence increases the total amount of classical information in the universe, while decreasing the amount of quantum information. This creates an irreversible flow from quantum possibility toward classical actuality that aligns perfectly with the thermodynamic arrow of time. Physicist Wojciech Zurek has shown that this alignment isn't coincidental, it's necessary. In his theory of quantum Darwinism, Zurek demonstrates that the information structures that survive the transition from quantum to classical must be compatible with increasing entropy. Only certain types of quantum information can successfully decohere into stable classical states, and these types always point in the same temporal direction as thermodynamic evolution. This selection process means that the universe's classical information has a built-in temporal orientation. The facts we can observe, the measurements we can make, the memories we can form. All of these classical information structures emerge from quantum processes in ways that reinforce time's forward flow. Reality isn't just consistent with time's arrow. Reality is continuously created by processes that define time's direction. The implications for consciousness are profound. Your subjective experience of time's passage isn't separate from the physical processes that create time's arrow. It is an integral part of those processes. Every conscious moment involves quantum to classical transitions as your brain processes sensory information, forms memories, and makes decisions. Consciousness doesn't just observe time's flow, it participates in creating it. Recent experiments in quantum consciousness research have begun to test these ideas directly. In 2020, researchers at the University of California, Santa Barbara, created artificial quantum systems that exhibit primitive forms of memory and decision-making. These systems show clear temporal asymmetries in their information processing, always forming memories of past interactions, while remaining unable to access information about future states. More remarkably, these artificial systems demonstrate a form of learning that appears to violate classical expectations about information processing. They can develop preferences and biases based on their interaction history, suggesting that even simple quantum information processors can exhibit behaviors that resemble consciousness in their temporal orientation. But the measurement problem reveals an even deeper puzzle about the nature of information and reality. If consciousness emerges from quantum to classical transitions, and if these transitions are what create time's arrow, then consciousness and time are fundamentally linked at the deepest level of physics. The universe's capacity to maintain temporal direction might be inseparable from its capacity to support information processing systems like brains. This connection suggests that the arrow of time isn't just a constraint that consciousness must work within. It might be a necessary condition for consciousness to exist at all. A universe without clear temporal direction would be a universe without stable information structures, without memory, without learning, and therefore without consciousness as we understand it. The measurement problem also reveals why the future appears open while the past seems fixed. Future events exist only as quantum possibilities, superposition states that haven't yet collapsed through interaction and measurement. These possibilities are genuinely indeterminate until they undergo quantum to classical transitions. But past events exist as classical information encoded in quantum correlations throughout the universe. This information cannot be erased or modified without violating fundamental conservation laws. However, this analysis of quantum measurement and information raises an even more fundamental question. If the universe maintains perfect records of its past through quantum correlations, and if consciousness emerges from information processing, what does this tell us about the ultimate fate of information, consciousness, and time itself in a universe that's expanding and cooling? The answer to this question reveals the cosmic scope of time as arrow and its implications for the long-term future of mind and meaning in the universe. Chapter 5. Cosmic Clock. The universe carries its own clock, but it's not the kind you might expect. Instead of ticking seconds or marking hours, this cosmic timepiece measures something far more fundamental: the progressive dilution of useful energy throughout all of space and time. Understanding this cosmic clock reveals why time has an ultimate direction that extends far beyond Earth, far beyond our solar system, and far beyond anything humans have directly experienced. A temporal orientation that will determine the fate of consciousness itself across cosmic epochs, stretching billions of years into the future. The cosmic clock began ticking at the moment of the Big Bang, 13.8 billion years ago. In that initial instant, the universe existed in a state of extraordinary energy density and perfect thermodynamic organization. All the energy that would eventually power every star, heat every planet, and drive every chemical reaction was concentrated in an incredibly compact, incredibly hot, incredibly organized state. The cosmic clock started at essentially zero entropy and has been steadily advancing toward maximum entropy ever since. But this isn't just abstract cosmology. It is the fundamental mechanism that drives every process in the observable universe. When stars form from gravitationally collapsing gas clouds, they reconverting the organized kinetic energy of the gas into the more dispersed thermal energy of nuclear fusion. When planets orbit stars, they're gradually losing orbital energy to gravitational waves and tidal friction. When life evolves and spreads across worlds, it's creating local pockets of organization at the cost of increasing the universe's total entropy. The cosmic clock explains why certain types of events can happen now but won't be possible in the future. Star formation, for instance, depends on the availability of hydrogen gas that can undergo nuclear fusion for the first time. As the universe ages and more hydrogen gets converted to heavier elements inside stellar cores, the raw materials for new star formation become increasingly scarce. Current models predict that star formation will essentially cease within about 100 trillion years, a deadline set by the cosmic clock. Even more fundamentally, the cosmic clock determines the lifetime of protons themselves. According to grand unified theories in particle physics, protons, the building blocks of atomic nuclei, are not permanently stable. They decay with an incredibly long half-life estimated at about 1,034 years. This is far longer than the current age of the universe, but it means that on cosmic timescales, even atomic matter is temporary. The cosmic clock is counting down to a future when atoms themselves will no longer exist. These predictions seemed like purely theoretical speculation until astronomers began observing the cosmic clock directly through studies of distant galaxies and cosmic expansion. In 1998, observations of distant supernova revealed that the universe's expansion is accelerating due to dark energy, a mysterious form of energy that appears to be inherent to space itself. This acceleration means that the cosmic clock is ticking faster than previously expected, driving the universe toward maximum entropy at an increasing rate. The acceleration of cosmic expansion has profound implications for the future of information and consciousness. As space expands, galaxies become increasingly isolated from each other. Currently, we can observe galaxies up to about 46 billion light-years away. But as expansion accelerates, the observable universe will actually shrink. Future civilizations will see fewer and fewer distant galaxies until eventually their observable universe contains only their local galaxy group. This cosmic isolation creates what physicists call cosmic horizons, boundaries beyond which information cannot travel due to the expansion of space itself. Once two regions of space become separated by a cosmic horizon, they cannot influence each other or exchange information. From the perspective of either region, the other has effectively ceased to exist. The cosmic clock is counting down to a future when all information processing becomes localized to increasingly small cosmic islands. But the most remarkable discovery about the cosmic clock came from studying black holes and the fundamental relationship between gravity, entropy, and information. Jacob Bekenstein and Stephen Hawking showed that black holes have temperature and entropy, with larger black holes being colder and having higher entropy than smaller ones. This discovery revealed that gravity itself participates in the cosmic clock. Black holes represent the maximum possible entropy that can be packed into any given volume of space. As the universe evolves, more and more matter will eventually fall into black holes. Stars will be captured or disrupted, planets will spiral inward, and even free-floating particles will eventually encounter black hole event horizons. The cosmic clock is counting down to a future dominated by black holes of various sizes, with most of the universe's entropy stored in their event horizons rather than in ordinary matter and radiation. The black holes themselves are temporary features on the cosmic clock. Hawking radiation causes them to slowly evaporate, with smaller black holes evaporating faster than larger ones. A black hole with the mass of the Sun would take about years to completely evaporate, an almost incomprehensibly long time. But stellar mass black holes are tiny compared to the supermassive black holes at galaxy centers, which may take up to 10,100 years to evaporate completely. This timeline reveals the ultimate fate toward which the cosmic clock is counting: a universe consisting entirely of elementary particles, photons, and empty space, all at thermal equilibrium with no energy gradients available to power any information processing. Physicists call this state heat death, not because the universe becomes hot, but because it reaches maximum entropy and can no longer sustain the energy flows necessary for complexity, life, or consciousness. The cosmic clock also explains why consciousness and intelligence are such remarkable phenomena. In a universe inexorably moving toward maximum entropy, the emergence of systems that can process information, create local organization, and even understand their own cosmic context represents something extraordinary. Conscious beings are essentially localized reversals of the cosmic clock, pockets of decreasing entropy that maintain their organization by accelerating entropy increase in their environment. This perspective reveals consciousness as a cosmic phenomenon rather than just a biological accident. Any sufficiently complex information processing system, whether biological, artificial, or something we haven't yet imagined, faces the same fundamental challenge: maintaining organization and functionality while the cosmic clock counts down toward heat death. The arrow of time isn't just the context within which consciousness operates. It is the defining constraint that shapes what consciousness can achieve. Recent research in astrobiology and the search for extraterrestrial intelligence has begun to incorporate these cosmic timing constraints. The Great Filter hypothesis suggests that there may be evolutionary bottlenecks that prevent most potential civilizations from developing advanced technology. But the cosmic clock adds another dimension. Even successful civilizations face ultimate limits imposed by the arrow of time itself. However, some theoretical physicists have speculated about potential escapes from the cosmic clock's constraints. Freeman Dyson proposed that sufficiently advanced civilizations might be able to survive indefinitely by developing technologies that can operate efficiently in the ultra-low energy environment of the far future. These technologies would need to process information extremely slowly to conserve energy, but they might allow consciousness to persist for arbitrarily long times. Other theories suggest that the cosmic clock might reset itself through quantum fluctuations. In the extremely far future, Random quantum events might occasionally create local regions of decreased entropy, Boltzmann brains, or even Boltzmann universes that spontaneously emerge from thermal equilibrium. If such fluctuations can occur, then the cosmic clock might be cyclical rather than linear, with entropy occasionally resetting to allow new eras of complexity and consciousness. But regardless of these speculative possibilities, the cosmic clock reveals something profound about our current moment in cosmic history. We live during an epoch when the universe retains enough available energy and organization to support complex information processing. When stars still shine, when planets can harbor life, and when conscious beings can contemplate their place in the cosmic order. This epoch is temporary, a brief interval between the Big Bang as initial organization and the heat death as final equilibrium. Understanding the cosmic clock transforms our perspective on human existence and consciousness itself. We are not accidental byproducts of cosmic evolution. We are expressions of the universe's capacity for information processing during its brief window of thermodynamic disequilibrium. Our thoughts, our discoveries, our attempts to understand reality are all part of the cosmic clock as grand progression from order to disorder, from possibility to actuality, from the mysterious past toward the inevitable future. Chapter 6. Temporal horizons. Beyond the edge of human perception lies a boundary that defines the limits of causality itself. A cosmic horizon where the arrow of time encounters the expansion of space and creates regions of the universe that are forever isolated from each other. Understanding these temporal horizons reveals how the universe creates its own future by making certain events impossible, certain information inaccessible, and certain causal connections permanently severed. These horizons don't just mark the limits of observation, they actively shape the flow of time across cosmic scales. The concept of temporal horizons emerged from Einstein's theory of general relativity, but their profound implications only became clear with the discovery of cosmic acceleration in 1998. Before this discovery, astronomers assumed that while the universe was expanding, gravity would eventually slow this expansion and might even reverse it in a big crunch scenario. In such a universe, every event would eventually be causally connected to every other event, given enough time. But the discovery that dark energy is accelerating cosmic expansion changed everything. This acceleration creates what physicists call de Sitter space, a geometric structure where distant regions of space recede from each other faster than light can travel between them. In de Sitter space, there exist cosmic event horizons beyond which information can never travel, regardless of how long you wait. Consider what this means for causality and information flow. Right now, there are galaxies so distant that while we can still observe light they emitted billions of years ago, any light they emit today will never reach us. The space between us and those galaxies is expanding faster than light speed, creating an expanding sphere around us beyond which events cannot causally influence our future. This sphere, called our cosmic event horizon, currently has a radius of about 16 billion light-years. But the most profound aspect of cosmic event horizons is that they not fixed, they shrinking. As cosmic expansion accelerates, our event horizon encompasses fewer and fewer distant regions. Galaxies that we can influence today will eventually pass beyond our causal reach and become forever isolated. The universe is literally tearing apart the fabric of causality, creating cosmic islands that can never again exchange information with each other. This cosmic fragmentation has revolutionary implications for the arrow of time. In a causally connected universe, time's direction could theoretically be defined globally. All regions could agree on what constitutes earlier and later based on causal relationships. But in a universe with cosmic event horizons, time becomes locally defined. Each causal patch develops its own temporal structure, its own arrow of time, potentially independent of other patches. The mathematics of this process reveals something remarkable. Cosmic event horizons themselves have thermodynamic properties. Just like black hole event horizons, cosmic horizons have temperature and entropy. When matter or information crosses a cosmic horizon and becomes causally disconnected, entropy is created. The universe generates entropy simply by expanding and creating causal isolation. This horizon entropy has been calculated by physicists like Raphael Bousso and Leonard Susskind. They found that the entropy associated with cosmic horizons will eventually dominate all other forms of entropy in the universe. As matter falls behind expanding horizons and becomes causally inaccessible, the universe loses information about its own past. The cosmic event horizons are not just boundaries in space. They read boundaries in time that actively erase the universe's memory of itself. But temporal horizons exist at scales much smaller than cosmic expansion. Black holes create their own event horizons that function as temporal boundaries within our local spacetime. When matter falls past a black hole's event horizon, it doesn't just disappear from view. It becomes causally disconnected from the external universe.